new one on particles independent of semi. I will not show yours off, but we want to have a design rule. What should the particle size be? I send it to you as a contact. You send it to all your friends in Japan. What should particle size be? Half the design rule or equal to design rule? It has cost money.
I didn't see you fix it.
Me neither. I didn't. But you're there. We are delighted. You are not a substance. You are a simple ring flavor. Give me your card.
Ladies and gentlemen, if you could grab some of the coffee and refreshment and you start settle back into your seat, we could get the next session started as soon as possible. Otherwise, we'll run into lunch, and you don't want to be rushed there either. Okay, we'll give everyone another minute to settle down. I know it's kind of difficult. The restroom is all the way around the other corner. I have to run back and forth myself. Okay, you have heard the overview. Covering all the way from the exploratory, the research type of new device structure materials, and also the down-to-earth manufacturing and fab operation, supply chain stuff. So in the next session, we'll try to get you to think about the front-end manufacturing technology. Again, there will be a lot of innovations that will be necessary, and there's a lot of opportunities there so that we can see how we can go from just the conventional bulk CMOS technology and overcome this brick wall. So the speaker will be Rin Cleveland from Texas Instruments. Rin right now is a manager of devices and manufacturing external R&D in the silicon technology development area at TI. He has a long experience in the industry, over about 30 years. And prior to this job, he was heading the International Semitech as a COO for all the process technology development programs for those advanced technology development factory. And he was also the director of front-end processing at Semitech in 1998. So without further ado, we'll get Rin to come up here.
Keep from tripping over this. I got it. Yeah. Okay. Good morning. I must first apologize. I think originally Alan Bowling from TI was going to give this talk, and he had a business commitment that kept him from doing it. So I'm here in this place, so I'm the backup in this case. I'm going to talk about basically the front end of the line today. You've heard sort of an overview of it from Bruce earlier, and some of the things hopefully aren't repetitive here, but maybe a little more in depth. But really look at a few things in terms of transistor performance and scaling challenges, and then some device architectures. You had a little bit of overview again in the earlier talk about this, but I'll cover just a little more there. And then a lot of the opportunities in the front end in terms of front end materials and modules. And then the front end is also, of course, driven, the gate length is driven very much by lithography. And just say a few words about that. I think what do I want you to get out of this talk in the overall is I think you'll see as we go through this, and as you heard in the earlier talk, the future in slang, the future ain't going to be easy. And it's going to be far from that. If you take a sort of an analogy with the back end of the line work that's been going on in copper low-K, for example, the back end of the line has been looking for two materials basically, and maybe some barriers, but they've been looking at copper, and then they've been looking at low-K materials, and really haven't got to that point yet. So they're only looking for two materials, and the material in the low-K dielectric, replacing the oxide, is really inferior oxide, right, compared to the front end of the line. So if you look at the, just an analogy of the work that's gone on in the back end right now to try and come to just finding these, getting these two materials to work and make them reliable and so forth, and that effort is really sort of, and you look at the roadmap, has been delayed even. So we're looking at challenges in the front end that on a high quality gate dielectric to replace it. We're looking at gate electrodes, we're looking at source drains. So you look at all the permutations and the new structures, the amount of permutations that we're going to be seeing is going to be huge. And to be able to do that cost effectively has also been a daunting challenge. So in general, I would say as you look at this talk today, it's primarily going to be looking at really how do we come across these challenges in a timely manner to make the stay on the roadmap. We've heard a little bit about Moore's Law already, but if you look at it, even Gordon Morse said in 1995, really the definition of Moore's Law has come to refer to almost anything related to the semiconductor industry that when plotted on semi-log paper approximates a straight line. So not only do we look at fabs, we looked at a while ago, the growth of fabs is exponential in cost. You can just look at all the various problems and issues in this industry when plotted and trying to stay on something. It looks like it's plots linearly on a semi-log paper. So one area there obviously is transistor performance. And if you look at that over the last few years, since about 1980, we've had some changes, but overall a sort of a trend up here, about a doubling every anywhere from 2 to 4 years. So we've had early on we had doubling about every 4 years. We went through a phase where the doubling was going up about every 2.5 years, and right now it looks like it's about every 2.5 years. And in the future, it's predicted it may be slowing down a little bit. So if we look at that, the transistor scaling has contributed to the overall improvement at about 17-19% per year, while the architectural design is also, innovations have contributed to another 13 to 21%. So you get an overall maybe 30% improvement. So if we look into the future up here, though, we're going to have some innovations that will have to come about, especially in the front end line, to keep the scaling improving at the rate that is being on at the current time. So this is the prediction Right now, and usually we use a term called FOM, or figure of merit, and if the frequency continues to follow that FOM curve, then it should do this with some improvement needed here to be able to stay on this current scaling. So what are the basic overall scaling challenges? I mentioned a few a second ago, but I'd just like to look at a very high level of this. We have isolation, of course, where we have terms of minimum pitch that has to be met. We have substrates and so forth in terms of isolation. We've gone through starting to implement silicon on insulator, SOI. We have, in terms of the gate dielectric, issues with leakage versus speed. As the scaling of the dielectric has gone narrower, thinner and thinner all the time, it becomes more leaky. And of course, in order to scale to get the speed, then we have to develop dielectrics that improve the leakage and still continue on the FOM curve. The gate electrode, because the polysilicon, we'll see in a few minutes that because of polydepletion, and also that which contributes then to the overall effective oxide thickness, along with the gate dielectric, it's really driving us towards a metal or a type of gate dielectric. And the questions come then: will it be a mid gap or dual gap or dual work function type of metal? So we'll be looking at that also. In terms of the junctions, of course, we've been talking about ultra shallow junctions, and I might call them super ultra shallow now, because as we look at some of the structures that we'll be talking about as we go through this talk, we'll also see that things like raised source drains will be required if we go to keep a planar structure and look at very thin silicon bodies. But in general, we have to have low series resistance contacts in order to keep the I drive for the transistor. And along with that, then not only low source contact resistance, but also the source drain extensions, as well as the source drain itself has to have very low resistance. And we'll see in the extension area, not only do we need to have it low series resistance, but we also need to have it laterally very abrupt in order to reduce spreading resistance, and also then vertically steep in terms of the extension of the transistor. So these are just a few of the high-level issues that we have to overcome, and those are what we'll be talking about today. If you look at the 2001 roadmap, the 2002 roadmap, as mentioned, has just been announced or released last week. But I want you to look at this one first, because really in the front end of the line, if you look at the major EOT, for example, and channel, the junction depths and so forth, and the wafer diameter and the gate length, those are really the things that really tied to what we're doing in the front end, and along with the chip power and power supply changes. So if you look at those, really from 2001 to 2002 release, there's only really been one change in the in these numbers, and that's really the 450 has been moved out. It was in 2013. It's been moved out to 2016. But the gate lengths that we mentioned or looked at earlier, the gate lengths here are the same as they were in 2001. The effective oxide thicknesses still fall in the same ranges, and the junction depths at the extensions are about the same. So there's really not a whole lot of change from the 2001 to the front end of the line in terms of requirements. So let's start looking at a few of these, and let's look at the first. The say is just a standard transistor that's been made for some time. The planar CMOS transistor can be described pretty much like this, where we have now STI is the isolation between devices. We still have junction isolation that we've had in the past. You have the gate dielectric here. We've been using halo type implants to suppress short channel effects and so forth. So in the standard transistor, we have this kind of device, basically, it's being used around everywhere. And what we're looking at is what do we do, if this scales to 65, what do we do beyond 65? Will it continue to scale? And so there's always issues as we thin and scale everything. We scale gate length and dielectric thickness, gate dielectric thickness, and so forth. As we do that scaling, then we run into several problems. One, obviously, as we lower not only a scale, but we also scale the power supply, and the power supply scale, I've been scaling also from 1.5 volts on down close to 1 volt now, 1.1 or so. So we have issues, of course, on threshold voltage in order to keep the overdrive and the VDD minus VT, it's decreasing as the power supply goes down and keeping in a reasonable VT to get the device turned off. Then we have a decrease in this gate or the overdrive of the device. We also have to be concerned about the sub-threshold slope in order to continue to be able to get the device turned off. And CD control, as mentioned earlier, in the earlier talk, that CD control will have to drive to various things like APC control and so forth to improve that. But it's not only in the litho part, but it's also in the etch and so forth, and the actual mechanisms that make the gate structure. So some of the issues related to the gate stack is that we end up not only the gate dielectric itself, we're starting into the direct tunneling regime, so the gate becomes leaky as if we continue to scale silicon dioxide or silicon oxynitride down. We start getting into the tunneling regime, not only for the gate, but also we have, as we scale the length of the transistor down, we also get into tunneling between source drain and band-to-band tunneling. So tunneling becomes as a key issue and to be able to turn the device off. Inversion layer, of course, as EOT, we reach some limit, then we can't continue to keep the inversion charge high if we can't continue to scale that down. Poly depletion, we also have issues with that as we scale. The thickness of a big part of the EOT, the effective oxide thickness, is made up of 3 basic components: the gate dielectric itself, but also the poly depletion contributes to that EOT, as well as the quantum effect in the channel itself continues to will also affect the overall EOT. So if poly depletion can't be mitigated, then that's going to essentially drive to ion reduction. As we try different materials to replace silicon dioxide, as we're looking at several now in the industry, going to higher K materials in order to thicken up the dielectric and to make it less leaky, then we have, we've seen anyway that most of these materials have inferior mobility as compared to silicon dioxide. And that mobility reduction, of course, then leads to an increase in the ion being reduced further. Of course, CD control of the gate stack itself, as these things get very narrow in the sub 100 nanometer range, then the CD control, not only from just the lithography, but the mass, the edge control, or edge roughness, and so forth, all of these things enter into the CD control. And of course, as these things scale, reliability is always a concern. If we look at the source drain region of this conventional transistor, then we have other issues. Of course, between the contact that's not shown here, across from the source to drain, series resistance has to continue to be adequate in order to keep I on, or if it continues to increase as it's doing now, then if we can't scale those junctions very well, then of course we'll have a reduction in ion. And the dopant profile of these extensions and the contact source drains also will have to be able to drive these to very abrupt. We have to have not only vertically steep junctions, but we also, and especially in the extensions, but we also have to have very laterally abrupt extensions. And of course, the contacts, as they shrink in size, become also an issue in terms of making good contact resistance. And of course, as I mentioned, the tunneling affects both drain to body and source to drain. So just to recap, just real quick, we have ion issues, basically, that I just mentioned. And I won't go through these again, but these are basically the issues that we just mentioned in ion, and then I-off is the other issue with the transistor that we have to be concerned about. So these are the things that are going to drive whatever material changes that will occur to stay in, say, a conventional type structure that we have now, or will drive us to new structures that have to try and mitigate many of these issues that we're talking about here. Well, in isolation, the roadmap has been, just quickly, we've gone from a locos type structure, which was used for many years. Some of us are old enough to remember this, but it's used for many years, and then we always, had the problem with bird's beak and so forth, and trying to reduce that. And then we introduced this shallow trench isolation to overcome the bird's beak. And of course, it had its own set of problems, as everyone's probably aware of. But it looks like as we go into the future, especially as we start looking at new structures and so forth on SOI and so forth, that we may end up with really sort of SIO isolation only, and even shallow trench isolation will be very minimal. And look at a gate scaling that we saw a while ago. This is the gate scaling curve where we, of course, the 99 values here, but this is the printed gate length and then the physical gate length and the X's here. This is out of the ITRS, the latest version. And we've been on, not too recently anyway, on about a 2-year cycle of reducing the gate effective thickness, gate length, the gate length here, on about a 2-year cycle of reduction. And it looks like if you look at 2004 out, it looks like we may be going back. It looks like it's, the ITRS anyway still says 3-year cycle. But if history prevails, we'll probably be potentially still on a 2-year cycle. I mean, that's, the ITRS says this, but history has been that we've been on this 2-year cycle now for some time. And before that, even faster than that. So all sort of, if you look at predictions anyway, we're on a 2-year cycle, and basically we could remain on that if the technology can provide the resources to do that. So if you look at this, also in terms of gate thickness, we talked about leakage a while ago. And if you look at the curves here, we have the oxide, of course, has been coming down, scaling down, as shown right here. And we'll see in a little bit there may be sort of a limit to how much you can scale this because of some physics in terms of, say, a conventional planar CMOS. And then we have also the leakage then shown here. This is where it sort of needs to go, and this is sort of, well, let me draw on here. The thick ox is here, and then the ITR sort of specifies this is the kind of leakage that we can support in the devices, especially, and this is, again, planar CMOS that we're talking about here. And if you look at, say, for an oxynitride, which is pretty conventional type gate dielectric now, is shown here. And you can see that at a point right here, these will cross over, and it says that at this point, oxynitride is even too leaky. And this is where we'll drive into the need for some kind of alternate kind of high K or higher K dielectric. So if we look at some device architectures and look at CMOS as we continue to scale, we've said we've been in this planar CMOS, and the question is how far can it be pushed? from the physics standpoint and materials and so forth. And the prediction is around, it's good for another 7 years or so. And this is possibly down to about the 45 nanometer node. Now, if history has anything to say about it, it'd probably go longer than that. People will get smart and figure out how to push it even further than this. But if you look at the physics and that is out there right now, it looks like there may be not only a need for near term for some material changes, such as the high K and maybe gate dielectrics and gate electrodes and so forth, but we may need to have an architectural change that will be able to extend CMOS technology further. And this has been sort of termed, at least the term we've used, is termed a non-planar CMOS. And this is in the area of using some type of a double gate process, potentially vertical. There's various kinds of non-planar devices being proposed, and we'll look at those in a little bit. And then if you look out even further, out past this, and we're not going to get into this part at all, we're going to limit ourselves to these two, but then we're talking some kind of new switch structure entirely is going to be needed, and potentially one switch that's being proposed and actually being in the research development right now is a carbon nanotube. Of course, there's many problems with this kind of device, such as how do you contact it, how do you lay it out, and so forth. But the potential is there. And there's many other devices that are also being proposed at this time. So let's look at some of these potential different architectures just for a minute. And they were introduced a little bit this morning. SOI was mentioned. The double gate structures are mentioned, and then I want to say a couple of words about memory innovations. And memory is important not only just as standalone memory, but it's also becoming very embedded in most of these other products. So let's look at SOI first. And again, the conventional device bulk CMOS is shown right here, with STI and the halo implants and of course the junctions are capacitively are connected to the bulk. If we take and cut this off, you can see we can build a box of oxide around the device, and basically by putting in a buried oxide or a box down here. And now you have the source and drain capacitively coupled through this higher capacitance to the silicon substrate. In this device, if this is kept relatively thick, and this is called the body of the transistor in this point right here, if this is relatively thick, then this will become what we call a partially depleted CMOS. So you can visualize this box of oxide around here that's isolating this particular device from all the other devices on the chip, and so the isolation now is basically this SOI. What's good here? The short channel effects are controlled, continue to be controlled by halo implants in this case. So that's not a change. So some goodness here is there's not a huge processing change in conjunction with using partially depleted in terms of what we're doing now with the bulk device. It does have reduced junction capacitance because we just said that this junction capacitance is much less than the other one using the oxide versus doing it directly to the well. And so that would imply that you would have better speed for the device, lower leakage, and so forth. Also, the device design translates straightforward into, like I said, the bulk processing goes right into this type of design. Complete isolation, as I said, this box is built around the device, so it's isolated from all the other devices. And these typically, because of the oxide thicknesses and so forth here and the thinness of this body, it's reasonably rad hard. So if we look at that partially depleted device a little bit more, of course it does have a body effect. It doesn't go, it's partially depleted, so it's not totally depleted in this case, so it does end up with this body region that has a floating nature to it. And so if we look at this depleted, the bottom junction capacitance are typically replaced by this thick oxide capacitance. The gate side lateral capacitances here are comparable to the bulk device, so there's not a lot of change there. Not that it's good, it's just not any change. But it can be smaller if this is thinned down, depending how thin you can make this, and that becomes a manufacturable issue of making this substrate. And if we can thin this down more, then you can even reduce that lateral capacitance. If you look at fully depleted device, we actually, what's happening here is just basically the body is getting thinner and thinner, and as soon as it'll reach a point compared to the gate length that it will become totally depleted, and which is this structure here, is if this thickness of this body right here, T sub SI, is thin enough. So the fully depleted device, again, it has the same junction capacitance as you did with the partially depleted with the source and drain and coupled through that. But the fully depleted film really suppresses this lateral junction capacitance a little better because of the thinness of this body. And we also have a speed improvement compared to the partially depleted device, and actually smaller power consumption, as we'll see in a second. So if you look at this, again, the partially depleted, we have this, of course, floating body in here, which can produce an extra node. You have, of course, the gate, source, drain, and the back bias, and then this floating node. So it has essentially 5 nodes, unless you can thin this a lot. The back and front gate are decoupled because of this internal floating node, and so obviously you have floating body effects. So the VT in this case is a function then of the voltage in the body, the floating body voltage. While in the fully depleted case, you have basically 4 nodes because this becomes fully depleted, so there's no floating body essentially there if it's thin enough. And we see that this, we'll see in a second, I'll show you again that it has to be thin enough that you get it fully depleted, but also it has to, of course, suppress short channel effects. If this gets too thin, the doping here being depleted is lighter, so you can get the interaction between source and drain easier in this case. So the neutral, there's no floating neutral region in this if it's thin enough, and so it becomes independent of the body voltage. And the subthreshold swing in this case on this device really begins to approach the ideal case of about 60 millivolts per decade. And in this case, we find the VT is directly a function of the backside bias. And this leads to devices like back bias devices, or back gate biases, devices, and so forth, as we'll see in a second. We also see with SOI there is a power reduction. This is a couple of papers that were presented a few years ago that in this case, it's a 0.35 micron SOI device, showing here the minimum clock cycle times. And you can see from the bulk device to the same device built on SOI that there is certainly an improvement in power. And a device that was built at Leti, here's the bulk device, and the device built on SOI fully depleted, and this is a 1/4 micron device. You can see there's a power reduction. If you take 1 volt here and look down, there's a power reduction of about 20% and a propagation time delay improvement of about 35% for this particular device. So SOI is clearly demonstrated its capability of improving power and performance. So if we sort of look at the merits of options that you could go towards below 50 nanometers, and I certainly haven't described all these options, but let's just look at some of these. The standard floating, fully depleted device has obviously strengths. It's small parasitic capacitances. It's a simpler device architecture. But it certainly has weaknesses, and we'll see that one of the key weaknesses in trying to scale to fully depleted is trying to make the thin body. And this is a thin body silicon on top of a barium oxide. And of course, there's different techniques that have been used to fabricate these kinds of devices or wafers, CMOS and also the bonding techniques. But in either case, this silicon film is going to have to be in the sub 50 nanometer thicknesses, as we'll see, and control of that to around 5 nanometers or 10% of that thickness, and be able to control VTs. So we'll see manufacturability in this case is really the key issue here, and can we build the substrates for this? Mentioned the ground plane device. If you have the thickness small enough, you can actually put in a back plane. For example, you could have the barium oxide made thinner, and right now it's reasonably thick, but if you could make it thinner, you could implant below that and actually implant a layer down there and make a back ground plane that you could, and if the box is thin enough, then you can actually control the device by biasing that particular backplane. And that has some advantages, a ground plane of some sort, depending on what type of ground plane, but it can lead to reduced short channel effects, because you still have short channel effects on these devices as you bring the gate length and scaling down. It does have a relaxed constraint on this thickness, because with the ground plane, then you can actually leave the silicon a little thicker, and versus the fully depleted where you don't have any backside. But with a ground plane, you do have problems with if the ground plane extends over and that is not self-aligned, for example, and is really not a back gate. If it's not aligned well, then you're of course going to have parasitic capacities, depending on, of course, many variables, depending on the box thickness and the ground plane, the voltages and everything you put on it. But you will have extra parasitic capacities that you'll have to contend with. And as has been seen with ground planes, subthreshold swing becomes greater. There is then, instead of a whole sheet or ground plane that you can bias, then there's the partial, and this is again trying to, the ideal case, and it really leads to a double gate. If you align the top gate with a back gate and you have that perfectly aligned, that becomes really a double gate. But if you let it be a little bigger and it's partially underneath the transistor, then it improves a little bit. You have, again, the problems with short channel effects, and you still have a relaxed constraint, but the parasitic capacitance is actually increased because of the coupling down to it. The double gate is really the one, is the best case, and that's where you do have a gate on the back side. You have the transistor and then another gate controlling the channel as you saw earlier, and we'll look at that again. But this is the best case for controlling short channel effects, because in this case the two gates then really take the field lines out of the drain into those gates, and so your short channel effects are improved because they don't couple then as well with the source. So you do have short channel control improvement in its best case. You have a little bit, again, a relaxed constraint on the silicon, the body, as compared to the standard floating device. In the standard floating device, we see that the thickness of this the body has to be about 1/3 the gate length to be fully depleted. But for this device, if you can go a double gate, then that is relaxed to about 2/3 of the gate length, and that obviously is much better. The issue here, of course, is in any kind of double gate device, as we'll see, is manufacturing. How do you fabricate these devices? And this is the real issue. And of course, there's still understanding to develop on the parasitic elements in these devices as you integrate them. It is expected, though, that a double gate device can scale further than, say, the planar CMOS device or fully depleted device. Right now, I think best modeling estimates are the planar CMOS obviously can scale down to 22 nanometer gate length, and the double gate devices easily will scale down a couple of nodes below that. Okay, so SOI fabrication issues, we'll get back to the double gates in a minute, but SOI, of course, is more expensive. It's 1.5 to 3 times the cost over bulk pricing at this time. The problem with SOI has been for a long time. It started, of course, back when CMOS was first done. And this is talking about etch bit density, or the defects, the threading defects and so forth that come up to the surface, are on the order of 600 to 1,000 per centimeter squared, which needs to be lowered yet. And a partial depleted, as we mentioned, and in a lesser extent, and maybe even no problem, if you really can get the silicon thin enough that's fully depleted, the body effects, floating body effects, have to be contended with in your designs. Fully depleted, as we mentioned, is really requires this silicon body thickness control, really on the order of 0.2 to 0.4 times the length, gate length. And I mentioned it's about 1/3, but that's about average between these. Some modeling shows you need to be on the lower end of this really to have good fully depleted devices. But to do that, you take an example at the 45 nanometer node, the gate length is about 18 nanometers. That means if you took the range for the silicon body thickness has to be in around 36 to 72 angstroms. So that's a 36 to 72 angstrom film on top of SOI, that's single crystal. So that's, from a manufacturing standpoint, that's going to be pretty tough. So that's the real issue in terms of fully depleted single gate devices, is trying to be able to make this thin film. Okay, well, one way around that is we mentioned that to get a relaxation on the body thickness is to go double gate. And so there's been, like mentioned earlier, several devices have been suggested. And this is one that came out of Berkeley and actually introduced earlier. But it's the FinFET. And in this case, this is the drain to source this direction, and this is a vertical fin that's cut first, and then the gate is grown and the polysilicon is put over it for the gate electrodes. Well, as mentioned, this fin, though, is the thickness of the body in this case. So it's a double gate device where you have the planar, now you have the double. that becomes really the thickness, the body thickness that you need. And as mentioned, it has to be, to get it fully depleted and so forth, it has to be around 2/3 the gate length in thickness. Well, this is a challenge because this is really sublithographic capability at this time. Now, early devices, of course, have been built by using sidewall oxide definition, and you take out, you leave the sidewall oxide standing on top of poly, then you etch that, and that sidewall oxide defines the fin thickness. And that's a possibility for manufacturing, but whether or not that's manufacturable on a large scale is questionable. So the primary challenge of this device right here is the formation of this narrow fin. And this is just an example of one of them that's right after fin etch, and the source drains and so forth still have to be made, but the fin is right here, and you can see the fin is right here, and you can see the gate that's been put over it. The gate is also lithographically challenging and etching that after you etch the fin. So in either case, this is a very difficult device to manufacture in volume. And just another one that was mentioned this morning is the Tri-Gate device that Intel announced, and I think has a paper here at this meeting. But this is a device that comes out of their earlier planar work where they were using a depleted substrate transistor, this DTS. And basically that's a thin body on top of SOI2, but instead here you make a device that's a double gate device on top of that using the same depleted substrate architecture. So the nice thing about this device, it does relax some of these dimensions in terms of the single gate of the fin itself. It's basically shorter, so it's not as tall, it's wider, and easier basically to fabricate. This technology supposedly also would incorporate high K, eventually to reduce, of course, gate leakage, and also adding in then epi source drain to improve the series resistance. And this is a cross section of it. You can see the body, the gates go around the side. You can see the gate on the side over here. It looks a little thicker than the gate on the top. But the three gates are this side, this side, this side. Provides the three gate. And this particular device was made with a poly gate electrode. So in it, characteristics obviously look pretty reasonable. So this is another approach that's being looked at. But what's the overall problems then with the double gate technology? It's getting this active area etches and so forth, where it's defined both the vertical gate and also the gate electrode itself has to be defined later, which is not insignificant in itself. The gate dielectric, of course, still has to be considered. The scaling of the gate dielectric may be relaxed a little bit, but it will continue on down, and then you'll have to integrate high K into this, and the high K integration is over a fin or a step, and that means conformality and other issues at that interface that have to be continued. You got corners now, and at the corners the VT may be changing a little bit, has to be considered and so forth in these devices. The gate materials and etch, of course, it turns out when you have it fully depleted, a mid-gap metal is probably adequate here, and maybe you can get away from the dual metal issue. So one attractive thing maybe about a double gate fully depleted device is that you might be able to go to a single metal, mid-gap metal to make the device easier to manufacture. Of course, you still have issues with junction and contact issues. The issues here, almost all of them, especially like the depleted, it will be thin out there. You have to use a raised source drain to make these devices manufacturable. And of course, that brings in a whole series of issues that will be continued with in terms of junction and the contact resistance. You still have the issue too of the very abrupt lateral doping that has to occur in this depleted area. This is also not trivial to get a very abrupt interface there from the source drain junctions to the body. And if you're looking at some kind of ground plane design, and if you're going to do this by putting a ground plane by an implant, then you start talking about other problems in the manufacture of the SOI in terms of the box thickness. The box thickness will have to get down in the 500 angstrom thickness with the silicon very thin on top of that, so that becomes another challenging thing for doing a ground plane approach. So just a quick overview here. It's listed here in this of different options that you can look at, from bulk all the way down to double gate with metal, a double gate approach with metal gates. And you can see the very interesting levels of doping that you can go with, mobility concerns. Mobility actually improves in these fully depleted devices. Of course, the mobilities, when you start doping the channel very heavily, then your mobility is going down because of that. And with the double-gated, fully depleted devices, you can use much lower doping or almost intrinsic body. The silicon film is a challenge, of course, with the double-gate devices, and certainly in the fully depleted device where you have to get very ultra-thin bodies. And the parasitic capacitors, of course, with many of these SOI technologies improve a lot because of the junction capacitances. And the performance, actually, of some of these devices are now beginning to be shown to be comparable or better than bulk CMOS. So, real quickly, just a couple of words on memory. And primarily, it's sort of a shift in memory. A lot of it's, of course, the need to embed memory in mobile devices or wherever. So there's lots of choices, and these are a couple of foils that came out of Intel, and I thought they were good in showing the overall approach. But in the desired attributes of future memory, really we still want low cost. Low power is a demand because of needing it for mobile applications. It needs to be really non-volatile for many of these applications. And it needs to be easy to integrate. And that's probably the key, hardest issue, is there's a lot of memory options out there, but how many of them are easy to integrate into this current CMOS structure? And whether it's a planar CMOS or double gate or whatever, it still has to be embedded. And you want to do this with only 1 or 2 mask levels in addition if you're embedded. So there has to be all those considerations. And if you look at today's memories, you have, of course, DRAM. Of course, it's volatile and it's difficult to integrate. You have SRAM. It's volatile too, but it's also costly. And you have flash, basically. And it's fairly slow in terms of write-read and cycles are limited versus some of the other memories that are being proposed. So if you look at some of these, there's various kinds of memories. The MRAM, it's magnetic memory. It's based on giant magnetoresistance application. Basically, it's a magnetic state. Allows electron tunneling to go on or off, so it looks like a resistance at the bit. There's FERAM or FRAM, which is some companies, my company in fact, is looking at seriously, or actually just announced. There's Ovionic Unified Memory, and this is really sort of a resistive heated spot, as you have this membrane right here, and you pass it over a resistive heated electrode, and it turns this to an amorphous substance at that point, so that becomes a change in resistance at that point. That's sort of like, think of that like a disc, but this could be actually fabricated into a device with cross elements heating this particular film. Of course, there's the flash memory, and in this case, the key advances in this is that you get multiple bits now at one bit. You have 4 states or so, and so you can improve the density. But the issue here is it's probably only scalable to about 65 nanometers. Then there's NROM, this nitride, a nitride gate type effect here where it stores charge at these bits. You get 2 bits per site in this case. And some polymer type works where the polarization changes with the switch here. All of these have their advantages and, of course, disadvantages. And the space that you're looking at in here is this space. Here's the volatile memory. You're looking at this space where it's really these non-volatile, low power, fast read-write cycles. So just looking at a couple of these, FRAM, for example, really is something like PZT or whatever, where you have a polarization effect. You polarize it, and the dipoles line up or down, and that's the states. Of course, the attributes of this, it is non-volatile. It has a fast read access in the order of nanoseconds. And the power is low in terms of nanojoules in read, a little higher in the write cycle. But it is fast write and read. It is a problem with being a destructive. Since this box isn't square, it can talk to its nearest neighbor, so you have to have a transistor to isolate it. So in that case, that is a negative. But in the other cases, it does beat the non-volatility. It is fast, and it is low power. The other one that's just mentioned is the magnetic RAM, the MRAM. And this is really a magnetic tunneling junction, or sometimes called a tunneling magnetoresistive element. And this particular cell is also non-volatile. It's non-destructive read in this case. It does have its low voltage and low power also, and a fast read write in the nanosecond regime also. And it has unlimited read-write endurance. Key issue here again is compatibility with embedding it into CMOS. So let's jump to the modules real quick. I want to talk about some front-end modules. And really we talked about substrates, gate dielectrics, gate electrodes, shallow junctions, and some edge control. If you look at sort of the history of high-level view of the history of substrates. Of course, we started with bulk silicon, and I'm old enough, some of you are old enough to remember all these, but then we had a whole sort of time of doing backside gathering and oxygen precipitation and so forth. Then we looked at reduced noise between devices and so forth, got into epitaxial silicon. And then recently, there's been more introduction now of partially depleted SOI. And a lot of noise going on even at this conference now with strained silicon. And usually it's some type of strain with silicon germanium relaxed, heterostructure in the channel. It's various ways of producing strain, but in the substrate it's typically of this type. There's other ways in process to induce strain. The partially depleted strained silicon is the next step. You take, of course, the partially depleted and put strain with it. Then you can end up with not only the properties of the SOI, but also the improvement from the strained silicon for mobility. Then there may be fully depleted and potentially fully depleted, then strained silicon is also possible. That's being looked at. So, and that list will go on, but these are things that are sort of in the area of substrates at this point. In terms of strained silicon, there's of course been work over the last several years on using a graded type of structure for strained silicon, where you start with a graded layer going from silicon, grading it up to about a 20 to 30% mix of silicon germanium, and then this layer tends to get relaxed. And of course, that particular material then has a lattice constant that's slightly different, a couple % different than the silicon, and so when the silicon is deposited on top of this layer, it ends up straining the layer, and that strained layer then, because of the biaxial stress and the energy level splitting, or NMOS anyway, improves the mobility at the interface with the silicon or the gate dielectric. So the key advantages here, you get an increase in effective mobility, and it's both seen if the dopant is, if the concentration of germanium is high enough for the P channel. Also, you'll get an improvement in the P channel as well as the N channel. The problems with it, of course, it's hard to integrate. Manufacturability, and of course this talks on manufacturability, but this is one of the issues with this. It's also whether or not it's compatible with future devices. If I go to ultra thin body and put SOI on here and go to thin body, can you retain the strain? If I remove the backside silicon germanium, will the strain remain on top of the silicon? Because you can't have the thin body any thicker than the strained layer if you go to fully depleted ultra thin body. So the question is, will it stay there if I selectively remove this strained, the silicon germanium layer below it? So its compatibility in the future is questionable. Also, if cost is always a problem. It's about a 50% cost adder now at 300 millimeter just for the wafer. So just a couple of pictures of strained silicon. You can see the strained layer here, the silicon germanium layer here with the gate dielectric. Again, this is one rim. Again, the gate oxide in here, strained layers. And this is a recent picture from Amberwave. UMC built this device, and you can see the strained layer here with the gate dielectric here. There's your L-shaped sidewalls again. Obviously, there's an improvement in mobility as shown by these graphs, both for the NMOS and the PMOS. And you can see at the low fields, down here in the low field area, you get an increase in the electron and hole mobilities, and you can see there's about a 1.8 times improvement with about a 30% germanium level here at the low field areas. So that's a significant improvement if you can withstand the cost of the added cost here. Now, of course, some companies are talking about other ways to induce this kind of strain, other than using the strained layer, and you'll hear more about that through the presentations this week. And I mentioned also that you could think about the ultra-thin body. If you can make an ultra-thin body strained layer, you can get and there's a paper that actually has shown some of this, that you can actually get both the strained layer and the ultra-thin body effect and get improvement from both. So not only do you have the goodness of the SOI ultra-thin body architecture, but you also get the strain in it. And the question always is, will this thin layer then continue to hold the strain? Just a quick thing on wafer sizes. I think it's covered earlier pretty much, but only thing I wanted to point out is that, and I said earlier that 450 is moved out. I did plot on here the recent 300 millimeter wafer levels. You can see at 200 and 300, and they're reasonably fitting the curve, although they're moving a little bit. But definitely 450 is moved out. So the projection now at ITRS is out in 2016. Gate dielectrics. I think there's been a lot said on this. I won't spend a lot of time on it, but of course we're going from silicon dioxide, where we've had a long history and reliability, but it has a problem with being leaky when you start getting below 20, 25 angstroms. In order to improve at least the boron penetration through these, the other issue here is boron penetration. People have put nitride in, which actually changes the dielectric constant a little bit. So the industry right now is on this oxynitride, and it does have low boron penetration. Reliability is good. But again, it's questionable if it's scalable below 10 angstroms. One high K material, higher K material, I'll say, is havium silicon oxynitride. Again, the nitride is put in, it's sort of havium oxide made into a silicate, and nitrogen added for boron blocking. This material looks reasonably pretty good. It's not really what I call high K, it's a mid-high K, a little above 10. It is scalable below 10 angstroms, and it has low boron penetration. It does still have a problem with mobility degradation of about 10 to 15%. So there's still work obviously to be done in the high K area before it's going to be implemented. And I won't go into all the possibilities here, but there's all kinds of high K materials being looked at. But I put this one up here, not because I'm from TI and we're going this direction, but it is one that looks pretty reasonable, and I had pictures of it. Here's another one I had pictures of, though. This is actually from Semitech. This is a havium oxide, and of course you can see the interface is quite thick here. It's because of the anneal and oxygen that was done, and to cause this growth at the interface. But if you look at it, and this has a metal gate on it, you can see the characteristics look pretty good with an effective oxide thickness right around the 10 angstrom value. So again, mobility degradation. This one doesn't have so much mobility degradation because if you get the interface oxide above 5 or 6 angstroms, then you don't have a mobility problem from the oxide, the dielectric. So if it gets much below that, then the interface needs to go down to almost nothing. And you can see, obviously, leakage is improving. Here's some examples versus, say, a silicon dioxide model. And it's getting close to the where we need to be. So if the target is around 1 amp per square centimeter as a target, then we're getting close to that with some of these dielectrics. IK manufacturability issues, of course, interface, dielectric preparation control, a high IK dielectric stability, the thermal stability of the high K dielectrics is always an issue because many of them change phases as you do subsequent anneals, and so you have limitations on what the thermal phase will be. Of course, they have material characteristics, and this is not only with the dielectric itself, but also with the gate electrode that you select with it. Boron penetration, again, is still an issue if you're using a poly gate versus a metal gate. IK dielectric interactions with a gate electrode obviously are problems. Many of these high K dielectric materials form silicides with poly, and that becomes an issue, as well as things like boron penetration. Some of these depositions to make these, some of them are put down with PVD, some down with MOCVD, ALD, various types of depositions. Every one of the depositions not only have complexities associated with them, but they also end up with different results. So you have different characteristics of the films depending on how you put them down, even in terms of mobility and so forth. Conformal depositions, of course, if they become non-planar, you have to contend with that, and especially over corners. Metrology, of course, of these films becomes an issue. And I just threw this in just to remind you of this interface. You have to think about this. If you want to end up with something around 6 or 7 angstroms, it's going to be very difficult to get there. Even if the interface dielectric is less than 1 angstrom, and the high K is 1 angstrom, effectively less. And if you have poly, you can't get it to 1 angstrom very well, so that implies some kind of metal gate to get it down to 0. And then the channel quantum effect typically is in 3 or 4 angstroms. So you add those up, that's 7 angstroms or so if all of these were met. And of course the interface right now isn't meeting this. The IK dielectric, obviously we're getting close to that. Metal gate isn't really, it probably will be found, but finding a dual metal gate will be difficult. And so a double gate device that could use a mid-gap metal would be great. So all of these really question whether or not you're going to get much below 7 angstroms as a gate dielectric. I'm running out of time, so I don't have time to go over all this very well, but I wanted to just mention why a metal gate electrode. Of course, the poly depletion is the key issue right here, because you get a depleted layer, and of course the centroid of the charge is up, so you get an effective capacitance up in this top layer, which adds into the capacitance of the dielectric, and then the quantum capacitance or inversion layer is down here. So you put all those together, and the effective oxide thickness grows larger, and so you'd like to get rid of this poly depletion, and of course the ideal there is you go to a metal gate. But choosing this particular metal gate is going to be the problem. And I've listed a few pros and cons with various things using N+ poly. Of course, then you've got a really high doping level. Or you have to go to something like silicon germanium to try and improve the depletion. But you'll reach a limit there. The mid-gap gate is good, but your problem there is you're going to have a VT is sort of limited at around 0.4 volts, can be lower than that. And the metal gate, the dual metal gate, is really the approach where you can put one metal at the valence band, one at the conduction band, and then you can get the expected results with no poly depletion. But the issue here, of course, is identifying this dual metal system. In terms of junctions, all I really want to say here is that if you look at the roadmap junctions down here, you can see there's sort of a barrier that's been sort of out there with any kind of anneal technology and implant technology, except for a couple where there's laser thermal annealing, but this has huge integration issues associated with it. And another one is really epitaxial growth in those cases. And if you really extend these boxes down, which is okay, then you can see the junction depths are okay for these. But these technologies to integrate these into the process in any near-term fashion is probably limited. So I would say that there's promise, but the sort of minimal progress to get below 65 for a manufacturable process for ultra-shallow junctions at the state right now without going to something like, and I'm talking about the extensions. And you can see from using the latest spike anneals that you can still see junctions out here in the 400 or 500 range. Sheet resistances are probably reasonable. A new technology that's been being looked at right now is really what's called flash anneal, and you can see there's certainly an improvement. And basically this is, as you ramp up to some kind of intermediate temperature, from a backside heater, and on a front side, you flash the front side, raise it up nearly to melt, and you can see the results there are looking fairly promising. Of course, ray source drain has been around for the contact area, and a lot of the issues with it, of course, there's many advantages. You have better contacts. You can reduce short channel effects. You can raise the contact concentration up. And it's going to be essential for any fully depleted SOI with ultra-thin body. And, but there's quite a few needs yet. Some of these are getting fairly well under control, like facet controls fairly well under control. But there's other issues still having a good manufacturable, low-cost process. And in terms of etch and sidewall, this is, just wanted to remind you, we're getting down in the widths here that are in the size of the molecules that we're talking about. So the line edge roughness is going to continue to be a significant issue. And that only propagates down into the etch. So they maybe have to come out with some kind of smoothing techniques, in other words, to improve this edge roughness on the gate stack. And just to remind you how thin these are getting, and metrology is important, and just mention that while I was at Semitech, we worked on a thing to actually develop these standards, and I just wanted to point out a 90 nanometer wide is only 293 lattice spacings in the lateral direction, not the vertical, the lateral, and so we're getting atomistic not only in the vertical direction but the lateral direction, and so you got to keep that really in mind. So any kind of etch and etch cleaning chemistries and so forth are going to, and the resist itself are going to contribute to this line edge roughness problem in CD control. And cleaning challenges, didn't even get into this, but there's all kinds of materials. All of these have their own cleaning challenges inherent to them. We're introducing all these new materials potentially in parallel, and the number of permutations, the way you can do things is just unbelievable. Scaling and defect levels are also, you've talked about contamination control. Not only is it particles, but it's also the materials introduce a lot of different kinds of contamination issues, and such as precursors and so forth, and the high K materials. And of course, ESH is always a concern. And lithographically, I just wanted to point out that even with 157, as we go down this trend, and we're getting out in this point here, 157 has to be introduced in the front end of the line at gate with phase shift technology and everything right from the get-go. So that's a real issue, and that's why there's been a lot of effort in looking at EUV, where you can get below this curve and get a little room to get back to, say, binary reticles and so forth. So this is a real issue that how do you get these technologies to extend? And it looks like got to do something that still works down in this area. And just pointing out that, remember, the K factor is the important thing that you got to look at. Even with 157, you can't get there. But the potential may be something like, in the near term, liquid immersion technology, where you can actually raise the NA and so forth of the technology, even back at 193. So, in summary, I think you've got to look at the problems associated with the front end right now. We've got numerous things to be looking at in the next few years in order to advance the front end of the line, both in terms of materials and structures. And so over the next few years, I think we're going to be seeing not only trying to extend the planar standard bulk CMOS technology as far as we can, but then the introduction of new materials such as strained silicon, SOI, and then driving into potentially, and which comes first will be debatable a little bit, but then into some kind of do a double gate structure that allows some of the standard materials to be used longer. So I guess from you look at it from an economics standpoint, the scaling of conventional devices will obviously continue as far as until they become impractical. We've said its analogy is like lithography. You know, we said it would become non-optical pretty quick, and it's gone on longer and longer. So devices probably tend to do the same thing in the device structure. But anyway, the scaling issues really fall into two areas, and that's materials and new structures. And either and both actually present huge problems for the industry. You won't be without a job for a long time. So with that, I think I'm out of time, even for the questions.